low oxygen levels, fish kills, and harmful algal blooms. What do all of these things have in common? Muck. On this episode, we discuss muck and all the problems this substance can cause in the lagoon and how important it is to remove it. What is muck and how do we get the muck out of here? Next on One Lagoon, One Voice.
Hi, I'm Dwayne DeFries, Executive Director of the IRL Council and the Indian River Lagoon National Estuary Program. Welcome to our One Lagoon, One Voice podcast. Each week, myself or one of my staff members will host leaders in the community, scientists along the lagoon, people who know a lot about the system to talk about some of the problems and, most importantly, some of the solutions to solve the Indian River Lagoon's health and make sure it's great for future generations. So let's get the show started and let's talk a little lagoon.
All right, to help discuss muck and some of the really important things that we have just recently learned about its properties, have Dr. Austin Fox from Florida Institute of Technology with me today. Austin's a biochemist and specializes in the chemical processes of muck, sediments, and the water column. Welcome, Austin.
Thanks for having me. Great to be here.
So, Austin, can you tell us a little bit about the organization you represent and just give us a brief hello to all our listeners?
So I'm an assistant professor of ocean sciences at Florida Institute of Technology, or Florida Tech. We have some really great programs, and one of the really cool things about Florida Tech is we have oceanographers, environmental scientists, and we also have an ocean engineering program. And so we have this kind of interplay between the research and the engineering. So when we need some equipment or something made that we don't have, we can work and we can solve problems pretty easily here. So some really great opportunities to do research. We're located kind of right in the center of the IRL. And so we have this great base of operations at our new Mertens Center. And so we have great access to the lagoon, which is kind of puts this great laboratory in our backyard where we can jump on a boat, go out for the day, and learn a whole lot about our lagoon.
Thank you. So before we jump into muck, and you just mentioned something about, jumping on a boat, I kind of want to reminisce a little bit about how you and I met and tell our listeners some of this. So about 10 years ago now, Austin, I remember being a grad student, and you, I think, were getting your doctorate under Treffery, and my wife, who was my girlfriend at the time, says, "Hey, there's this great college role position available. You should go check it out." And I walked into Treffery's office, and I think you were bouncing around, and it was a job to do mapping of muck in the IRL. So we've kind of come full circle here, where back then I was doing some probing, taking the FIT boat out, driving it around, testing for muck, and you were wrapping up your doctorate. So it's funny how the small world it is. Now that we're talking about muck, let's have you kind of explain what muck is. What is it in its simplest form? Where does it come from?
So that's a great question. And I think there's a few different kind of perceptions of muck, right? As scientists, we have this very specific, it's this and this and this definition. But to the public, to most people, if you walk in the lagoon and you step in this gooey, smelly stuff, right? That's muck. So that's kind of that everyday definition where I don't need fancy equipment to tell you it's muck. And then we have the kind of compositional definition, right? We take some samples, we bring them back, and we analyze. And there's three things that we're looking for. The first one is that it's greater than 75% water by weight, right? And so if you actually take the muck and you dry it out, it will shrink a lot, and you're left with actually very few solids. And so it's mostly water. 10% or more of the mass of the dry solids is organic matter. And then 60% of the particles are small enough to be considered silt or clay. And so that mostly water, greater than 10% organic matter, and silt and clay sized particles are those compositional definition. And so again, that black gooey stuff is kind of the easiest to explain to somebody. It's been described as black mayonnaise. Most people have probably smelled that hydrogen sulfide or that rotten egg smell that comes from it. And that's the anaerobic decomposition that occurs in that muck. And then as we start to map it, so you mentioned our work 10 years ago.
Yeah.
It's kind of funny. I was out on the boat this afternoon with one of those same poles. So cool how life comes full circle. And so that's actually yet another definition, right? It's a lot of work and a lot of cost to go out and collect and analyze these physical samples in the lab. And so just poking it with these sticks, and it's a process, right? You get good at it and it's pretty precise. But that's yet another definition. And so one of the things we've worked really hard to do is link these definitions, right? How much can that probe go in before it actually fits that compositional definition? And it's interesting. If the probe goes in more than about 30 centimeters, it's very likely to be muck. When the probe goes in less than about 30 centimeters, so for most people that's a foot, then it's actually likely to be some kind of gooey sediments, but not quite fitting those definitions that we call muck.
That's interesting because I remember when I was probing, I get sometimes just the very bottom of the probe would come up with a little stickiness on it, and it was black. Like you'd think it was muck, but per this, definition, it might not have been muck, or could it have been some spreading out from these places where it comes from? And we'll talk about that in a minute. So where does this stuff come from? I'm sure it's not natural bottom. It shouldn't be in the lagoon. Where is it coming from?
So that's a great question. There are natural components to muck, and I'll come back to that. But most of what we think of muck today has come from over a century of human activities. And so it kind of began in really the 1920s. I mean, there's some evidence of redirecting water and adjusting our watershed before then. But really in the 1920s, we started to dig channels and drain the wetlands near the St. Johns River for agricultural purposes. And this redirection of stormwater brought with it fine particles that are both naturally occurring in the soils, but also as we disturb those soils, we're causing those fines to be released and they wash into the water body. And so that's part of it. Remember, 60% of this stuff is just that fine-grained, again, only 10% is organic matter. And so that fine-grained particles that are disrupted by moving of soils is a large contributor. And then the organic matter that's in it has come from, again, that over 100 years of human activity adding nutrients to this system, right? Adding organic material to the system. And so if I tell you 10% organic matter, you might think of sticks and leaves and twigs. But if we actually look at muck, the organics aren't like discrete pieces of organic matter, right? It's these organic molecules that have coated the surface of those inorganic particles, which causes some challenges when we think of mitigating this stuff, right? Because you can't just go pull out the organic piece of it. It's intermixed with those inorganics. And so over time, those inorganic particles have become coated with the organics, and they're very fine. And if you imagine you go to the beach and you stir up the sand, the large particles are going to settle out quickly, and the finer the material, the longer it stays resuspended in solution. And so this stuff is easily resuspended. And so if it's in shallow areas, it gets mixed back up relatively easily. And so it slowly migrates and accumulates in these really deep deposits. So the deeper areas of the lagoon are where we tend to find this muck.
And you just hit the nail on the head on my next question. I was going to say, where do we find a lot of this stuff? But it seems like the deeper stuff, canals probably, and where a lot of these outfalls, because that's kind of the transportation, right? All these stormwater outfalls is where a lot of these fine sediments are coming from, right?
Absolutely. So we see a lot of it in canals and in places where there's an outfall that this material is coming in, fertilizer, potential, basically any sources of nutrients or organic matter. And then it does migrate to the deep areas. And so some of the recent work that we've done, we've been trying to identify, is muck all the same? And it turns out that it exists on a gradient, like many things do. And we're finding, if you had to break it down into kind of two broad categories, we've termed these discrete and continuous muck deposits. And so those are terms from the geological literature, but continuous is where we have basically a really broad, deep area of the lagoon where it's naturally deep and we've accumulated the fines. As you move to shallower and shallower water, the grain size tends to increase as we move into shallower water with higher wave energy. And this muck in these continuous deposits tends to be less organic rich. It tends to have more coarse-grained material intermixed, and the the benthic fluxes, right, the adverse impacts of it tend to be a little bit less. And then we have what we call the discrete deposits. And so these tend to be in anthropogenically created deep areas. So if we've dug a canal or we've dug a hole to take the dirt to fill land or to build a causeway, those are these really nice deep areas, and they've accumulated those fine-grained materials. And the muck that we find in those areas tends to be a lot finer grained. It tends to have much higher organic contents. We're often seeing up to 20% organic material in those muck deposits, and the adverse impacts tend to be a little bit greater in those discrete deposits.
Perfect. Let's talk about impacts because you just mentioned them. Why is muck such a problem? How does it influence the system a little bit? Tell our listeners why it's so bad.
So the best way to visualize this is I think a lot of people have had a compost pile at some point in their life. And that's effectively what muck is, right? It's this organic rich material that is sitting there decomposing. And as it decomposes, it's releasing the nutrients, right? And so if you have a compost pile at home, you're breaking down the organics to release the nutrients to then put on your plants. In this case, it's just sitting on the bottom, decomposing, releasing nutrients, feeding all of the different things in the lagoon. Hopefully it would be seagrasses and all of that stuff. But unfortunately, when there's too many nutrients, we start to see things like algae and phytoplankton dominating, and that can contribute to some of the poor water quality.
Sure. So, you talked about nutrient fluxes or nutrients. I know these things also flux these nutrients. So they're not just kind of steadily releasing them. They can have massive pulses. Can you touch a little bit on that, on what that means and that process?
That's a great question with a lot of little rabbit holes we could go down. So in essence, this muck is to some extent continuously decomposing and releasing nitrogen and phosphorus. But if we look at sediments in general, so we move to something that's not muck yet, right? So if we look at kind of healthy sediments in the lagoon, we do see them behaving as a sink, right? So in a healthy estuary, the sediments house bacteria that actually carry out a series of processes that remove nutrients. And so this is termed nitrification, which takes the reduced forms of nitrogen that come out of organic matter as it decomposes, oxidizes it to nitrate, which is probably a form of nitrogen a lot of people have heard of.
Mm-hmm.
And then once we've gone to nitrate, we can carry out a different process, different set of bacteria that carry out denitrification, and they can convert that nitrate into N2 gas. And N2 gas is inert, it's not bioavailable, and it will diffuse back into the atmosphere, not leading to any adverse problems. And so this is the hope, right? This is what estuaries are supposed to do. And in healthy estuaries, this process actually helps to remove a large fraction of the nutrients that come in through stormwater before that water is discharged into the coastal ocean. Because estuaries are just that area where rivers empty before it moves into the coastal ocean. What we're seeing here and what people have seen in other places is as the sediments become less healthy, we start to see changes in the bacterial populations within the sediments. And so we're seeing less nitrification happening. And that's the aerobic bacteria, right? We're seeing less of those aerobic bacteria that kind of kick off that process of nitrogen removal. And as we see less of those, that nitrogen is staying in the lagoon as bioavailable forms that are able to feed algae and those kinds of things. So as much as I talk about muck and muck being a problem, the thing that I'm worried about is as we see the muck becoming intermixed with those healthy sediments, we're going to start to lose the ecosystem services that are carried out by those sediments.
Gotcha. And so you just touched on a couple of words and something else that muck is really bad for, and I want to touch on. So you mentioned aerobic bacteria, which is they use oxygen, right? So then there's anaerobic, which is no oxygen. And one of the other side effects of muck is hypoxia. Can you talk a little bit about how that occurs in muck?
Yes, great question. And so this has been kind of an iterative process in my life here. I started out studying muck, and we've spent a lot of time learning and understanding the muck. And so that's how we started to think about those healthy sediments. And I mentioned that as we lose those nitrifying bacteria, we start to recycle nitrogen within the system. So those aerobic bacteria are dependent on the availability of oxygen. And as we have more organic matter entering the lagoon and being recycled through bacterial processes, they're consuming oxygen. And so when we have the water column running low on oxygen, that's what we call hypoxia. And we define it depending on who you talk to. It can be 2 or 3 milligrams per liter, depending on which process you're interested in.
Right.
But in essence, it's just low oxygen causes problems in the environment with the fish, right? If we have low oxygen for a couple of days, we'll start to see fish kills. My interest are the things that don't make the news. So the fish can get up and swim away, and so it takes a relatively large area going hypoxic for us to actually see a fish kill.
Mm-hmm.
But it's the things that can't get up and move that I'm worried about. So I'm looking at the infauna and even the epifauna, the crabs and the things. I'll go to a site and I just see dead crabs, and I see dead infauna, dead whelk. Those things don't make the news, but that's pretty telling to me, right? That tells me we've seen a pretty significant hypoxic event that may have come on slowly enough the fish could have left. And yeah, new infauna might come in, but it does take a toll on the bacterial populations, right? We're going to see a change in the geochemistry, the bacterially mediated geochemistry happening within those sediments. And it can cause the nitrogen to be recycled versus removed.
So, that's really interesting, and I'm glad you were able to elaborate on that. So what I want you to kind of tell us about is some of that work, what you're learning that's like kind of big aha moment, like kind of tease sediment oxygen demand is a big one that you've been really looking into, and changes, and you kind of mentioned it already, the changes in sediment chemistry. So just go ahead and tell us about some of that new work that you've been doing the last couple of years and the big aha moments from it.
We started out looking at benthic fluxes, and so that's the nitrogen and phosphorus. And as part of that, we were looking at how much oxygen is being consumed as we decompose this muck. So we got these, what we call sediment oxygen demand, a measure of just how much oxygen are the sediments consuming. And it can be really high, right? If we look at the sediments, if we take a really mucky deposit, it could consume all of the oxygen from the water column. It depends on where we are and how deep the water column is, but it can be as little as a few hours or as long as a couple of days. And the reason we don't run out of oxygen is because there's photosynthesis in the overlying water and there's wind mixing oxygen back into this water column. But that really got me thinking, is the organic matter in the lagoon causing us to see hypoxia? And so we started measuring oxygen at the bottom at a few of our sites that we were studying the nutrient fluxes at. And we started to notice that the DO at the bottom looked a lot different than the dissolved oxygen kind of at that mid-water column. And it makes sense because if you think about what is using the oxygen, so the bacteria that are decomposing things, those are really concentrated at the bottom. But it's interesting because if we take a YSI or a sonde or just an instrument that measures dissolved oxygen and we lower it from the boat, it takes a couple of minutes to do it right, it may look like the oxygen's pretty well mixed. But if you actually let that instrument sit on the bottom for a few minutes, we actually start to see that oxygen tick downwards, which is really interesting to me. And what we're learning is just as that instrument goes down through the water column, it's pulling with it. It's causing some turbulent mixing and it's bringing oxygen from the surface down with it. And so we're seeing this kind of boundary layer that exists towards the bottom of the lagoon. And so we realized that you can't use just this single moment deployment of a YSI or an instrument to track this hypoxia. And so we started using these bottom water dissolved oxygen loggers and deploying them in as many places as we could. And it was kind of shocking to us how often we were seeing hypoxia. And when we talk about hypoxia and fish kills and things, I think most people are aware of the dead zone in the Gulf of Mexico.
Right.
And so for a few months each year, most years, the farmers are applying fertilizers to the crops in kind of the Mississippi watershed. It rains a lot in the spring, that washes nutrients down, bringing a lot of nitrate into the Gulf of Mexico. And then all of that decomposing organic matter leads to hypoxia, right, or lack of oxygen in the bottom water in the Gulf of Mexico. And this wreaks havoc on the fishing there. But that lack of oxygen lasts a few months. And so you can take a ship and you can drop these YSIs down and then move to the next site, and a few hours later drop it down again. And over a couple of weeks, you can map the aerial extent of this hypoxia. So as we move into estuaries, we're noticing, right, you can't even drop it at a single place and get a good reading. So how are you going to do this all over the place? And so we're building this network of these sensors. And we have, at any given moment, it's expanding, but we have like more than 20 sensors out there now. And we plan to pretty significantly increase that number in the coming months. But the really cool thing is we're seeing these daily changes in oxygen. And so in the middle of the day, the sun's up, we have photosynthesis occurring, and we're seeing the oxygen increasing, as you'd expect. And then at night, the bacterial respiration and even respiration from the phytoplankton lead to this oxygen going back down. And this happens every day. And that's what we call diurnal or diel hypoxia. And it's interesting, as we see algae blooms happening, we're actually seeing the oxygen go way up, right? And maybe way higher than we would expect it to be during the day because there's so much production in the water column.
Mm-hmm.
And then at night, that oxygen is consumed and it gets lower than we might expect. And so we're actually in many places in the lagoon, especially during the summer months, seeing diurnal hypoxia almost every single night. A lot of places in the lagoon are seeing at least a couple hours of hypoxia. And that's concerning. Because again, the fish can swim up, they can swim away, but the infauna, the things that can't get up and move, how are they being influenced by that? And so that's really what we're starting to dig into. So at this moment, our real question is just, well, how big is that aerial extent of hypoxia? How long does it last? And what are the implications of these chronic short-term hypoxic events?
Yeah, that's really interesting. You know, I wouldn't have even imagined for an estuary that's on average 4 feet deep to have these really stratified, heterogeneous levels of DO, and that you could change it just by dropping, your sond in. That's pretty wild. What does this all mean to the healthy sediments and eventual restoration that's going to start ongoing with seagrass planting? How impactful are these chronic acute hypoxic events that are happening almost every day? How's this going to impact those efforts?
I think it's going to be huge because until recently, most research is done during the day. Most people are going out and dropping their YSI and they're seeing
Yeah,
that the
good point.
oxygen's high. And so now by being able to say there is this hypoxic event occurring, that's really informative. So we've started to think about, okay, what are the implications of hypoxia? And obviously other places have gone through hypoxic events and seen the impacts on seagrasses. And so hydrogen sulfide, which we've touched on earlier, is toxic to humans, right? It's toxic to fish, it's toxic to infauna, and it's toxic to seagrasses. And it's formed, again, in anaerobic sediments where just bacteria are carrying out their normal metabolism. And when there's no oxygen, they use alternate oxidizing agents, one of those being sulfate, which is salt, right? It's using one of the
Hmm.
salts that makes up 8% of the salt in seawater, and it's converting that sulfate to hydrogen sulfide. And so that's that rotten egg smell, totally naturally occurring. It just means that we have a lot of organic matter decomposing. But that's toxic. And if that's becoming more present in the sediments, that can actually make sediments toxic to seagrasses. And so if we look at kind of some of the approaches to seagrass, where should we expect seagrass to come back? We're often thinking we may see it recovering in areas where it used to be. And it is possible that an area where the seagrass used to be has now experienced enough hypoxia that the seagrasses have gone away, and the depth at which we find sulfide is actually migrating upwards. And that may make it much more difficult for seagrasses to recolonize those areas. And so this is something that's been seen in other places. Like there's models from Laguna Madre in Texas where they're imagining that a relatively significant portion of their seagrass was lost due to the initial light limitation from algae.
Right.
But then they're thinking that the majority of the biomass loss was actually resulting from that hydrogen sulfide that resulted from it.
I was just gonna say that's huge. I mean, everybody kind of blames these algae blooms, and like you said, that probably was the initial shock that knocked all our seagrass back. But from what you're telling me, this muck and this organic matter, this hypoxia, is really kind of what's keeping it from coming back. So it kind of tells me, this is a huge problem, and so it kind of segues into my next thing is how do we mitigate this stuff? How do we get it out? Are there ways to stop it at the source? What do we do?
So that is a great question. And I stop and ask myself that all the time, right? I say we're identifying these issues, and sulfide is one of the issues that we see happening with hypoxia and with the problems we've seen in the lagoon. And I stop and I say, how do we remedy this? And if we just go back to seagrass example, so seagrasses actually help to mitigate the sulfide in the sediments that they're living in, because seagrasses create this relatively low energy environment between their roots, and so they actually contribute to the accumulation of fine sediments in the seagrass beds. Right. So if you talk to seagrass scientists, they'll talk about how the sediments used to be squishy and organic rich where the seagrass was, and when we lost the seagrass, it actually got harder. We actually lost some of that organic material.
Mm-hmm.
But the seagrasses photosynthesize, they create oxygen, and they actually pump some of that into the sediments using their roots and rhizomes. And that actually helps to detoxify the sulfide. And so it's interesting, just the presence of seagrasses can help to detoxify the sulfide that might be occurring for a variety of reasons. The other piece that we are really interested in, and so this is why we're looking at kind of the impacts of chronic short-term hypoxia, is one of the other things that detoxifies sulfide is reactions with metals. And so there's iron that comes into our lagoon through groundwater and surface water, right? If you've seen a fence around Florida that the yard's watered with groundwater, it's stained red because there's so much iron in our water. But when we see hypoxia, we talked about this anaerobic bacteria. One of the types is using that sulfate. There are other types that use iron, and they effectively take an iron 3 that exists as this amorphous iron complex that actually has charge sites that can bind things like phosphorus, and it changes that, and it becomes reduced to an iron 2. Iron 2 reacts very strongly with sulfur, with hydrogen sulfide. That process, right, the iron reacting with the sulfur actually helps to remove and mitigate the toxicity of that sulfur. But at some point, the iron that is contained in those sediments can run out.
Gotcha.
And so if we have chronic hypoxia that's happening for just a short period of time each night, is it possible that we're just losing small amounts of iron over time, or iron and other metals that are capable of absorbing it, and eventually we've lost that capacity to detoxify sulfide? So we've started down that road, right? So you're seeing that there's lots of questions coming out of
Sure.
this.
Oh, yeah.
And we've started down that road, and it's kind of shocking how there's very little bioavailable or labile iron to be found in lagoon sediments. And that's very likely the result of chronic short-term hypoxia.
So there's another innovative idea out there that some people may have heard about, some may not. Just want you to touch on it, is capping. And could you put iron in that cap to help maybe facilitate this process?
So that's a fantastic question. And I think we have many tools available to us for restoration, and I don't think there's any single right answer. So I think dredging has some real benefits. I think capping can be a great addition to that. So there's a few capping projects that have happened in the Southern Lagoon, and they've been pretty successful. And there's been capping, a little tiny project up near Titusville, and there's been capping done in other places, right? It's not this new idea.
Hmm.
And there's many different ways you can do it, and there's different additives people can add. So people can add iron, people add, and you name it, people have tried to add it to solve some of these problems. But yeah, absolutely. I think some amendment to the capping. So normally they're using quarry sand. So basically sand from a place like the lagoon that's now up on land. They dig out sand and spread it over the top. And it's interesting because the specific quarry that sand came from may have an impact on its ability to sorb things like phosphorus. So that's just something we should be considering. And then absolutely, I do think there's amendments that we can add. And I will be the first person to tell you I don't like the idea of adding artificial stuff to try to solve a problem, right? That's going to cause different problems later on. But the really cool thing is iron and these iron oxides are a naturally occurring mineral that is found in our soils. And so we can basically select a more iron-rich, naturally occurring sand for these capping type projects, or we can supplement the sand that's available locally with something that would contain something like iron or something else that's totally natural.
Gotcha. Is there anything else that can be done for muck? Typically, it's dredged out and it's put into what's called a DMMA, or a dredged material managed area. And you were doing some work on trying to increase the efficiency of the nutrient removal from the water, because as we know, it's mostly water, and or if we pump a DMMA full, it's eventually going to overflow because it can't carry all of the water. So we want to try to clean that water that's coming out so when it goes back in the lagoon. So talk a little bit about that work that you did in the DMMAs.
So we were, again, trying to understand the natural processes that happen in the lagoon and how they're influenced by changes in the availability of oxygen is what we were working on. So we're trying to understand how increasing the oxygen concentration would promote those natural processes to see if we could have the largest improvement possible, right? So the lagoon has a lot of nutrients in it. If we're testing how much nitrogen can we remove, and the lagoon might have 1 milligram per liter, then we can only remove 1. But if we go to these DMMAs, they may have higher concentrations in that water, which they're treating. So we went to one of these DMMAs where we could get the highest concentrations of nitrogen we could find to just see how effectively we could remove it. And so we were just testing it, and then a DMMA contractor was like, well, can you remove this much? And we said, we're not really trying, we're just trying to understand the system, but we could help the system and actually probably do that. And so we looked at what does it take for these bacteria that live naturally in the sediments to do their job. They need food, right? They need some kind of carbon source. They need nutrients, which is what we're trying to deal with in the water, so that's available. And they need oxygen. And the other thing they need is somewhere to live. And they live on surfaces. And so they live on the particles of the sand. They live on pretty much any surface you give them. And so we started to look for surfaces. So if you look at a bioreactor that is just promoting these natural processes, they use a type of, they call it media, right? Which is just the material that you're giving them to live on.
Yeah.
And we searched high and low for what the best media was. We tested all kinds of different compounds, things that had been used before: wood chips, zeolite, perlite, biochar, maize cob, all kinds of different stuff. And it turned out that when we use a plastic material, which is what is used in commercial bioreactors,
The
we
little
were
bio
able to,
balls. That's right. Yeah.
so bioballs, right? It worked really well. The problem is, as an environmental scientist, I'm not going to go purchase plastic to be manufactured to throw into our water treatment system.
Yep.
So we brainstormed, and eventually the idea came out. One of my students came up with the idea of using plastic bottle caps. And we tried the bottles themselves, but just not the right plastic, and there's potential for degradation. So it turns out the bottle caps are actually made out of the same materials, so polypropylene and high density polyethylene, which are the same materials used in these bioballs, and they're in theory free. And it's repurposed, which, if we go back to our reduce, reuse, recycle,
There you go.
repurposing is actually better, right, than recycling, because there's no energy involved in that repurposing. So we went to the public and we said we need help collecting these things. And it turned out to be a fantastic outreach program, right? We were able to connect with the public. And most importantly to me was it was people who wanted to help the lagoon, but they might not have had the ability to go walk in the lagoon and help with some of these restoration projects. It might have been people who were just didn't have the ability to actually go get their feet wet, but it was still a mechanism for them to help. So we collected tons of bottle caps and we were using them as a substrate to grow the bacteria that would naturally be living in the sand. And then we created an environment where they had all the oxygen they needed. We gave them all of the carbon they needed. We let them process the nutrients. And it turns out that when you give them all the things they need, they do their job really well. And so, from my perspective, we're using this to understand how to restore the natural sediments. So I would love to not have to have a substrate. We just use the sediments as a substrate and we
Hmm.
figure out how to make that happen. But we were able to put this in a water treatment system, pump water through it, add the right amount of carbon, add the right amount of oxygen, and we're removing over 95% of that nitrogen in as little as 5 minutes.
That's amazing.
It's just unbelievable how well nature works when it has the tools it needs. So how do we make the sediments, how do we restore that ability to our sediments? And so that's kind of the mission we've been on. And then why have our sediments lost that ability? Because when we do the calculations, and stop me if I'm going on too long here, but we were like, this is great. We can treat the whole lagoon using bottle caps. People love it. And at 1 million gallons per day, which is like a full-size wastewater treatment plant, it would take about 400 years to process the water in the lagoon.
That's a long time. I'm not going to be around for that.
And so all of a sudden, right, it's just not this practical large scale solution. There are absolutely applications to water treatment on small scales in localized places, right? There's absolutely solutions for those issues. But we need to be thinking bigger and we need to think about, well, if we have the whole bottom of the lagoon, 400 square kilometers of lagoon bottom, and we can restore these ecosystem services to those sediments, that's huge. We could be processing the whole lagoon in a matter of hours if we're able to restore those natural processes, right? And that's the dream.
Yeah, for sure.
So
what could our listeners do? I mean, obviously bottle caps is great, but is there something they could do, on their house to kind of stop their input of muck? Because I'm sure everybody's got to playing a role to that input of muck a little bit.
So that's a great question. And I guess I have to give a shout out to all of our outreach partners and people. So like the NEP is doing a fantastic job getting those messages out. So same things you're hearing, right? Fertilizer, you don't need it. That's just a huge one. I think about how much work it is to remove a pound of nitrogen, and then I just cry to see that you can run over to Home Depot or Lowe's, not being partial to any place you could get it, and it's just so easy to get. So it's so unnecessary for lawns and those kinds of things. I mean, I really like the idea. I'm working in my yard to get it kind of natural vegetation. So we just shouldn't perpetuate that green lawn idea. I think that's kind of on the extreme end. And we're seeing projects to remove some of these normal lawns and put in new bioswales or natural kinds of vegetation. So I think that's really helpful. And then check your septic systems, check all of that stuff, and then support science. Right? I think that's a huge one.
For sure, we're learning so much, and just what you've told me today is, I'm sure a lot of people have never heard this information. So definitely science matters, and it's going to hopefully give us the tools to right these wrongs down the road. So awesome.
And so just touching on that, right? We're doing science and there's actually applications of this, right? So we're saying, how do we fix these sediments? How do we make them do the job they're supposed to do? And one of the things that we're realizing is that in fauna, we're losing those through these hypoxic events. If we can restore the infaunal populations, they dig, and it's really easy to overlook the importance of those diggers. But things that stick their little paws in the sediments, I know they're not paws, right? But dig around in the sediments actually help to pump oxygen through that boundary layer at that sediment water interface. And that can help get that oxygen into the sediments to promote that decomposition of muck, to promote those healthy bacteria, to promote these processes over large expanses of lagoon. And so this is something that we wouldn't know anything about, right, had it not been for research. And then the really cool thing, the thing that I'm more excited than probably anything about, is working with our restoration partners, right? You're hearing about people starting to do clam restoration, right? You're starting to hear people put things back in the sediments that are going to disturb those sediments. And I'm really excited for that potential. And the science can help us figure out where to put those things to be most effective. And so we can use the science to help the restoration that will then help the science. And it's this feedback loop that I think has incredible potential. And I think just really supporting those efforts is great. We're learning so much is being done. And I really feel like there's hope. The seagrass that I'm seeing right now is pretty amazing.
That's great that you mentioned that, because I think a lot of us are starting to see those little signs of hope, and after a decade of pretty bad times. So that's great. And you just gave me an idea too for our next podcast. We got to talk to Holly Sweat over at the Smithsonian, because she does a lot of work on that infaunal community. So there's a good idea there. Just want to say thank you for your time. This has been an awesome discussion. I'm super stoked, and I really want to see the new stuff that we keep learning about the sediments and the lagoon and how that can play into a role in restoration. So thanks, Austin. Really appreciate it.
No, thank you for having me. This is great. And we enjoy being able to share the work we've been doing. So thank you.
Great.
And you should talk to Holly.
For sure.
I've been talking to her for years about how can we connect the geochemistry to the infauna, and we just got a project through DEP going where we're actually going to look at infauna and hypoxia and geochemistry at the same sites. So
excellent. Can't wait to see the data. If you enjoy these discussions about the IRL, please like and subscribe to this podcast. To learn more about the Indian River Lagoon National Estuary Program and how you can get involved, and tips on living lagoon friendly, or to purchase One Lagoon merchandise, visit us at onelagoon.org. And our newly redesigned Indian River Lagoon license plate is now available at your local tag office. To stay informed about lagoon news and upcoming events, follow us on Facebook, Instagram, and YouTube at One Lagoon.